Did it start at 9 a.m.?
No, you're in the wrong one, buddy.
Why did he send me a link for a 9 a.m. Zoom meeting?
Don't know. But I can't hear anything.
Then he probably hasn't started yet. Alright, so that means I'm
Let
gonna...
me try this.
There we go. Now I hear him. Yeah. Go to the
Better
Zoom.
now, right?
Yes.
I'm doing
Okay, okay. Let me mute everybody. If you can hear me, I guess it's there was something to do with my computer here, but I fixed it. Thank you. Thank you. So let me just go back to what I was saying. I was making an announcement regarding the ongoing quiz. Let me mute everybody so that, you know, we don't get interruption from the background noise. There is an ongoing quiz. I posted the periodic table. I'll recommend that please make a copy of that periodic table. You're gonna be using that for the exams, all right? I will also, I know some of you, you may not have access to printer in your home or where you are. I'll recommend that try to talk to somebody to help you, or maybe go to office Max and get a copy of the periodic table and the formula sheet, which I will also share with you regarding the exam next week. I will share the study guide as well as the formula sheet, which you will need before the exam. You realize I didn't give you in the quizzes I expected you to read. I'll give you the formula sheet. For example, how do you change the temperature in degrees Celsius to Kelvin and so forth? What is the formula for determining the atomic weight given the naturally occurring isotopes with their percentages? You know, there is an equation for that. How do you find the subatomic particles? That's the mass, number of protons plus number of neutrons. I'll give you the formula sheet. Density equals to mass over volume, all those kind of things, so that you don't spend time trying to think. So how will you do that? Unless you print out ahead of time, you won't be able to use any other resources during the exam. That's what I wanted to point to you, that you need that periodic table. Please print that periodic table. Also over the weekend, make an effort to printing the study guide for, not a study, yes, you may print the study guide, but the formula sheet. The exam will cover up to wherever we will stop today, not what we will cover this coming Thursday, all right? What we'll cover on Thursday, I want to give you 1 week to prepare, almost like a week, yes, starting from today. So I intend to make a short quiz on chapter 3, not the entire chapter 3, but wherever we'll stop today. That's what I want to point out to you as you prepare for the exam, what you expect, and how to prepare. Somebody's asking, so we can print a formula sheet for, you can print a formula sheet for the exam, all right? You realize that I didn't give you for the quiz, so don't expect for the quiz, but for exam, I expect you to have the periodic table as well as the formula sheet. That is for exam, but for this quiz too, you need the periodic table. You know, I don't expect you to memorize, the entire periodic table. Some information, you need to have the periodic table before you, okay? Ronnie, you need to have a periodic table for quiz too, but not, for exam, I'll give you the formula sheet, but you don't need the formula sheet for quiz 2. All you need for quiz 2 and quizzes is the scratch paper and the periodic table. The scratch paper and the periodic table. All right. So make sure you have those before you get started with quiz 2. Without wasting my time, I don't want to go back to what we talked about last time. If you have any question, you can use the chat feature. I'll be toggling between the two as we go along. As far as our lecture today, I want to go straight to chapter 3, which is reaction, chemical reaction, and chemical reactions and reaction stoichiometry, chemical reaction and stoichiometry, which I know you covered reaction and stoichiometry in Introduction to Chemistry. You covered that in Introduction to Chemistry, so I know this chapter is not new to you. Let me just share my screen so that you can, we can all follow along as we go with our lecture. Any question on the exam? I noticed that, you know, so far, some people, they use the, they take, you know, less time in answering the quiz. I don't know if you, you rushing, or, you know, the exam is, or the quiz is easy. Please spend some time in answering those questions effectively. Use the allotted time frame. So let me just share the screen here. I'm gonna share my screen with you so that you see the PowerPoint slides, chapter 3 on chemical reaction and solutions, chemical reaction and stoichiometry. In particular, what I'll want to show you the roadmap for chapter 3 is in section 3.1, what we look at is basically how to write the chemical equation. Chemical equation represent chemical reaction. Chemical equation represent chemical reaction. You know how to interpret a chemical equation. Reactant on this side, product on this side. That's what we'll be looking in the section 3.1. Section 3.2, simple patterns of chemical reactivity. There are some patterns. For example, decomposition of hydrogen carbonate. There is a pattern for that. There is a pattern for decomposition of carbonates, hydrogen carbonate. There is a pattern for reaction of acids, all right? We'll come back to what we covered in chapter 2, formula weight, all right? How to determine the formula weight given the periodic table. Look at the concept of the mole with respect to Avogadro number. We'll look at the calculation, empirical formulas, and analysis. It's different from the empirical formulas in chapter 2. We will now calculate. In chapter 2, given the formula, you just simplify, but given the masses, how do you determine the empirical formula of a compound? Section 3.6 is quantitative information from the balanced equation. So if you had a challenge in balancing the equation, please, it's time to jump on it and teach yourself until you master the concept of balancing equation. Quantitative information. If you are given this amount of reagent, how much of the product do you expect from the balanced equation? Now, that will lead us to the limiting reagent and excess reagent. That will lead us to excess reagent and limiting reagent. It's not always that when you are given reagent in a balanced equation does not mean that all of them will run out. That's what we're gonna be talking in section 3.7. Now, what is stoichiometry? Stoichiometry is basically, it comes from the Greek term stoichion, which is basically quantitative. This stands for quantitative relationship between reactants. Should have keep this so that you see that reactants. That's what I meant, reactants and products and products. That is the limiting reagent, excess reagent, when we look at the relationship between products and reagent, that means you are doing the quantitative measurement relationship between reagent and our product, which you are expected to know from a chemical equation, A plus B going to C. You know, these are the reagents, this is the product, or we may have even more product on that side. What we are doing here is quantitative relationship. Sometimes you may have gone to shopping, you don't take everything, fill the shopping cart. You compare what you have on your card versus, you know, what you want. That is a shrewd way of looking at the quantitative or stoichiometry area of which examine the quantities of substances with respect to what is consumed in a chemical reaction. Here is an example of a chemical reaction. When you do that, you are looking at stoichiometry. We need to be familiar with what we talked about, the law of mass conservation in chapter 2, based on the law of mass conservation, which says that matter cannot be created or destroyed. Antoine observed this when he decomposed calcium carbonate. The mass of the starting reagent was equal to the mass of the product. So this stoichiometry is based on the law of mass conservation, that matter cannot be created or destroyed. This was the foundation of stoichiometry. You need to remember what the law of mass conservation state. Now, having said that, a chemical equation represents a chemical reaction, and you should know, or you should be able to interpret. A, you should indicate the state plus B. We're gonna talk about this later on. I know you know what L stands for liquid. Going to C, I may also have that means aqueous plus D, and I may have this is as gas. What you see as subscript are the physical states of reagent A, B. Sometimes you may see something above the chemical R right there. It means there is a catalyst. This is a generic chemical. This is a generic chemical equation. It represents chemical reaction. We often use, you know, chemical equation to represent chemical reaction. This is interpreted as A react with B or A combined with B, all right? The arrow means produce, to yield, okay? To give. And something above the arrow means a catalyst, and then this gives C and D. The subscripts indicate the physical state, and you should be able to interpret what those mean. So the arrow separate product from what? From the reagent. The arrow separate product on the, this we cannot call these reagents or reactants. Sometimes these terms can be interchanged. Reactants, and what we have here are products. These are products. On the left side, I mean on the right side of the reaction arrow, on the right side of the reaction arrow is the products, okay? Products on this side. You have 1, 2. This is something you already done. Addition means, you know, react with. I know in math means you add this to that, but means in chemistry it means A and B are reacted to give C and D. Here is just a generic chemical reaction for A and B, all right? A and B to form C and D. H2O is produced when oxygen gas reacts with nitrogen gas, all right? These are the reagents or reactants, the same thing to give a product here, or products. Product for 1, product for 2. You should know what or where the reagents are product. If we flip the equation, it's still gonna be the same thing. C plus D going to A plus B. If we flip the equation, whatever we have on this side will be the reagents. That's the rule of thumb. Anything on the left side of the reaction arrow represent reactants. Anything on the left side of the reaction arrow represent reactants. Balancing the equation. What is balancing the equation? What is balancing the equation? So reagents and reactant are the same thing? Yes, it's the same thing. Santi, it's the same thing. Reagents and reactants are the same thing. So I know at some point you may see worded problem and you may wonder what is the difference between these? They are the same thing. Coming back to balancing the equation, to balance something is to make it equal, you know. The concept of balancing equation is making sure that the atoms, all right, the atoms on either side of the reaction arrows add up. For example, here, let me just use H2O. Hydrogen gas react with oxygen gas to produce, remember gases are the atomic oxygen gas, not O as atom, to produce H2O like this. Assuming that you don't know anything about the balancing the equation, you may think that this is okay, but the number of atoms on either side of the reaction arrow, the number of atoms on either side of the reaction arrow in this example here do not add up. If you look at the hydrogens, here, we have two. Remember how you read these? Two hydrogens, two oxygens, and these two applies to hydrogen, not oxygen. So I'll read this as two hydrogens, two hydrogens. Two oxygen, there is one oxygen on the right side of the reaction arrow. Balancing the equation is based on the arrow on either side. You see, this is where we are, our reference is the reaction arrow on either side. So the equation is not balanced. How do we balance? We balance the equation using what we call coefficient. Coefficient is a number which goes in front of a reactant or a product. In this case, we need a 2 in front of H2O to make the number of oxygen equals. The 2 here applies all to hydrogen and oxygen. So I'm gonna read this as 2 times 2 hydrogens. We have 4 hydrogens on the product side. We have 2 on the reactant side. So I'm gonna go and put a 2 in front of hydrogen gas to give me 4 hydrogens. So I'm gonna use a check mark that hydrogens and hydrogens are balanced out. If there is nothing, it's understood that it is 1. We say that the equation is balanced. Why do we have to balance? Look at the slide, because of the law of mass conservation. If we don't balance the equation, we are contravening, we are breaking the law of mass conservation, which states that matter cannot be created or destroyed, all right? You cannot destroy atoms during a chemical reaction, So here is, all right, if you see C pillar for H2O right here, you start. I use H2O here to show you the concept of balancing. It's just trial and error. And we call these numbers right here coefficient. These are the coefficient, the numbers which goes in front of a reagent to balance out. Methane and oxygen gas, all right, you have to account for the number of atoms on either side until everything balances out. We say that the equation is balanced out when we use the coefficient. Now, subscript, don't change the subscript during the balancing of the equation. You cannot change the subscript. Otherwise, you'll end up with the wrong formula. You cannot change the subscript. Let me go back to the previous slide. Previous slide here. Right, let me go back to the previous slide right here. Anthony, you have a question here? Is it a slide on my whiteboard or? Okay, all right, thank you. Somebody was writing notes. Yes, thank you. So this is the slide you're referring to. This is basically showing the reaction between methane and oxygen gas. Reaction between methane and oxygen gas. What this means is you'll be given this, in case you're wondering where those numbers came from. This is oxygen gas to produce. This is to produce, not to give. Let me walk you through. H2O, this is H2O liquid, and CO2. Let me walk this. I'm gonna solve this. You start by balancing an element by element. Doesn't really matter where you're starting from. I can start from carbon. Here, let me start with the carbon. I have one carbon, I have one carbon. So let me just use a check mark that carbon is taken care of. Next is hydrogens. I have 4 hydrogens here, but here is 2, there is nothing else. So how do I make hydrogens equal on either side of the reaction? Remember, this is where we are facing. I need a 2 in front of H2O, so that hydrogens, 2 times 2 is 4, which will balance out the hydrogen and hydrogen, hydrogen and hydrogen. That will take care of that, all right. And here, let's see oxygen, 2 times 2, all right. 2 times 2, 2 times 1 is 2, plus 1 is 3. So we need a 2 in front of what? You need a 2 in front of oxygen. Somebody say that we need a 2 in front of oxygen to make it equal. Thank you. That's just you go through. Thank you, Ali. That's how you go through trial and error. Just you encourage, you don't have to memorize like, okay, let me see, maybe it's gonna ask me this. It is just trial and error. And if you look at this, it's maths, and maths, you don't read maths, you practice maths. Unless you do a couple of examples, it will be a challenge. So I was talking about the subscript and coefficient. What is a coefficient? A coefficient is a number which goes, is CH4 gas for the equation? Yes, this is gas. Yes, this is gas. We're gonna talk about the physical state, it is gas. I'm talking about the coefficient and the subscript. If you change the coefficient in an equation, it will alter, all right, or it will mess up the chemical reaction. You never balance the equation by balance or by using a subscript. Let's see what happened if you change the subscript. H2O is produced when oxygen gas react with hydrogen gas to form H2O. Let's see. If you are given that equation, let's say this is liquid. Watch out when you change the subscript. You don't change the subscript. The subscript, if I put a 2 there, somebody might say, let me put a 2 there. This is wrong because this is peroxide. What you end up with is a different, totally different compound altogether from what you are given. Never balance the equation by changing the subscript. You always use a coefficient. A coefficient is a number which goes in front of. So we call the number which goes in front of a reactant or a product a coefficient. a number which goes in front of, all right, a reactant or a product is coefficient. Never change the subscript. Subscript, if we have a compound such as this, let me show you how you interpret a subscript. It applies to everything in parentheses. If you have something like this is interpreted as 2 oxygens and 2 hydrogens. It applies to everything in parentheses. We read this as 2 hydrogens, 2 oxygens, all right, and 2 hydrogens. The subscript here applies to, all right, it applies to both hydrogen and oxygen. So you got to make sure that you know how to interpret or what the subscript means in a balanced equation, H2O, all right, this is a coefficient, this is a coefficient. If there is nothing in front of a reactant or a product, it is understood that it is only one. So don't balance an equation by changing the subscript. You will have mess up the chemical equation. That's one thing you need to remember when balancing equation. We don't change the subscript errors. It will change the compound you are intending to produce in a chemical reaction. Here is the previous example on reaction between methane gas and oxygen gas. Burn, the coefficient are used instead of just changing the coefficient. I mean the subscript, use the coefficient. Well, that is all about the balancing the equation. How do you balance? By making sure that the coefficient or the coefficient you use gives you the total number of moles on either side. The states of matter, if states can either be liquid, this stands for liquid, you know that. G stands for this is gas, that means gaseous state. S stands for solid, that means it is in solid state. Or commonly you will see this means aqueous. Aqueous means dissolved, this means dissolved in H2O. This means dissolved, all right, dissolved in H2O. That means water has been used. Aqueous means dissolved. These are the common physical states you will see in chemical reaction or chemical equation, and they are represented in what? In parentheses, Antonio, how do you know not to write 2 in front of a subscript? How do you know? Well, how do you know? It is only one way. All right, the only way you balance an equation is to use a coefficient by placing in front of a reactant or a product. The only time you write a subscript is when you are writing the chemical formula, you know, when we get to the double replacement reaction, when you switch the ions, or when you're writing the chemical formula, is when you put the subscript. For example, I don't want to say that you don't write a subscript, but you have to be able to write the correct formula of the product. For example, if calcium product, calcium hydroxide is a product, all right? I'm just giving you an example on when to write. Calcium hydroxide, somebody might say calcium hydroxide look like that. No. You have to know that this is in group 2, hydroxide is a polyatomic ion, all right, hydroxide, and the correct formula for your product in this case is this. This is the only time you will write or you will use a subscript to write the chemical formula, but not to balance the equation. So here I was writing the formula for my product, but I've used a subscript. It does not mean that, oh, if I write a subscript, it's gonna be wrong. No, when writing the correct formula of the product first, or the correct formula of a reagent, using what we learned in chapter 2 is when you use a subscript. But when balancing the equation, only a coefficient is used. You do not use a subscript. You do not use a subscript. So you write, first of all, the correct formulas of the products or reagents, and at that point, you may end up using a subscript to write the correct formula for your product. So you do not write a subscript. Remember, Antonio, don't change the subscript. It's only that when you are writing the correct formulas of your product. So coming back to the states, these are the common, all right, these are the common physical state you will see, including what I talked about in the previous slide. Aqueous means dissolved in H2O. Aqueous dissolved in H2O. Most solution you will encounter in chemistry are aqueous solution. That means water is used as our solvent, You got to know what those means, all right? If you have an arrow above, if there is a triangle above an arrow, it means either you hit the reaction is heated, or if there is an element placed above the arrow, say for example, if I put PT, for example, platinum, or I may have iron like this, for example, it means a catalyst has been placed. It's not a big deal. No one will ask you that, but so that like, do I still need to use the element above the reaction arrow? You don't use those elements. All you have to worry is the products and the reagents All right, let's see. On this slide, balancing the equation, I'm just giving you a simple one, CO2. All right, let me see CO2. CO2 gas plus O2, this is gas right here, to form CO2 gas, CO2 gas. You use trial and error, all right. You use trial and error by saying, okay, I can start with carbon and say one carbon on the reactant side, one carbon on the product side. Use a check mark. Next is oxygen. So I'll combine oxygen here on the reactant side. This is how you look at it. Oxygen is 1 plus 2. You have 3 oxygen on the reactant side. 3 oxygen on the reactant side. Versus, all right, versus 2 oxygen. This is now what you need to look at. You have to, not the coefficient. I mean to say this is 2 right here. You need 2 oxygens. So the equation is not balanced. The equation is not balanced. You have to go back and forth. It does not mean when you balance one element, it will balance the whole equation. So I may say, all right, let me put a 2. All right, if you put a 2 in front of, all right, if you put a 2 here, you may want to leave the oxygen first. If I put a 2 there, that means I have 2. I have 2 oxygens plus 2, 4. So if I put a 2 in front of 2 there, so 2 plus, that's 4. If you look at the number of carbons here, 2 carbons, 2 carbons. 2 oxygens plus 2 oxygen is 4, so I have 4 oxygens on this side. And on the product side, 2 times 2 is 4 oxygen. The equation is balanced, 2 and 2. So you need to use trial and error until you end up with the correct number of atoms on either side because of the law of mass conservation. So you need a 2 in front. The other one is aluminum. Aluminum. We have 4 aluminums on this side. Al or Al4 solid plus H2O. This is a liquid to produce aluminum hydroxide, AOL 3 plus CH4. You don't need to, you may be given the chemical formulas, but sometimes, down the line when we get to chapter 4, you are expected to know, how did we end up with 3 there? It's because of aluminum is positive 3, hydroxide is negative 1, we end up with that. So 4 aluminums on this side. If you look at the number of aluminums, you have 4, we have 1 on this side. We have 1 on this side. So how do we balance the equation? If I put a 4 here, this 4 applies to aluminum, it applies to hydroxide. So if I look at the number of aluminums, there are 4 and 4 aluminums. I use a check mark when an element is balanced out. When an element is balanced out, I use a check mark. Now the carbons on the product side, all right, I have 1 carbon. This is 1 carbon. It balances out with 1 carbon right there. So I use a check mark for carbon. But when we get to hydrogens, on the reactant side, I do have 2. Let me write down 2 hydrogens because of these 2 right here. But watch how you handle parentheses and the coefficient. These 3 right here, you read this as 3 hydrogens times 4, we have 12 hydrogens there, 12 hydrogens. All right, 12 hydrogens. That's how you read the interface product. Somebody say there are 3 couples. Oh, yeah, there was 3 couples right here. Thank you, Shari. So we have 3 right here. I messed up from the word code. There is a 3 there. Yeah, so there is a 3 here. I missed that. So it's gonna change the equation. Let me back up then and look at the, I'm gonna look at the couples. We have 3 as a subscript right here. So let's see the couples. Couples right here is, we have 3 couples and 1 here. So we need a 3 in front of, methane gas. We need a 3 in front of methane gas. And by the way, this is gas. 3 and 3 balances out. So we got to do that. We got to do that for carbon. Hydrogens, 2 times 1, there is a 1 there, 2, you say 2 hydrogens. So I have 2 hydrogens on the reactant side versus how many hydrogens I have on the product side. 3 times what? In parentheses, yes, it does. Kenneth, they aren't in the parentheses. We don't have parentheses. Shadi, yes. No parentheses. So 3 times 1, 3 hydrogens times 2, we have 12 plus 12. So there are 24 hydrogens on the product side. How do we, what do we need to multiply by 2 to give us 24 hydrogen? We need to multiply by 12. So we need a 12 in front of H2O. And remember the 12 applies to oxygens as well. So we read this as 12 times 1 oxygen. We have 12 oxygen on the product side. We have 12 oxygen on the product side. I mean, on the reactant side, but on the product side is 3 here times 1. 3 times 1 is 3 times the 4 coefficient here give us 12. So the way it is the equation is balanced. So I have 1 right there. All right. There is 12 in front of H2O. There is 4 in aluminum hydroxide, and there is 3 in front of methane gas, and the equation is said to be balanced. The last one, C solid zinc. All right, solid zinc reacts with sulfuric acid to form hydrogen gas, and aqueous solution of zinc sulfate is produced or to form. Example C, I wanted you to see that or understand that it's not always that you are given given chemical formulas in the problem A and B, you are given chemical formulas. But sometimes you may be given worded chemical equation and you are expected to interpret it and write the correct formulas of your reagents, correct formulas of your products. Otherwise, if you don't know, and then the concept of balancing equation will be at all on your side. So please learn. You are expected to have learned in chapter 2. The coefficient, all right, before I look at C, somebody is asking the coefficient. This is 1 right here. I meant to say 1. When there is nothing, it is understood to be 1. It is understood to be 1 right there. All right. I've seen problems, asking, what is the sum of the coefficient when the following equation is balanced? Problems on balancing the equation is, what is the sum of the coefficient when the following equation is balanced? So you have to add 1 plus 12 plus 4 plus 3, all right? And if you don't understand that 1 is in front of aluminum, somebody will say 0. 0 times any number will just be a 0. So Christian, it is 1. Fast forward to C here is understand that at some point you will be required to interpret a worded chemical equation, write the correct formulas for ionic compounds, for molecular compounds, for acids, name them, whatever we learn in chapter 2. For this problem, it is solid. Okay, I want to use a different color on my whiteboard. Zinc, all right, solid, react with, means plus. Sulfuric acid from chapter 2, this is the formula for sulfuric acid, and it is aqueous. To form zinc sulfate, predominantly zinc form, positive, zinc positive 2, sulfate is negative 2 polyatomic ion, and it is given the physical state as aqueous. And then hydrogen gas, it is not, I see common mistake students make is giving hydrogen atom in a state of hydrogen gas. So that is the gas. And you are expected to balance. Sometimes the equation could be balanced. For example, this one is balanced. I can tell you that. We have 1 zinc on this side. We have 1 zinc on the product side. 2 hydrogens, sulfur, sulfur, and oxygen, oxygen. The equation is balanced. Sometimes it's balanced. Yes, Crystal, wouldn't the coefficient be 6 in front of reactant H2O? Let's see. It could be 6. Let me see. Yeah, you could be right. So if we put here in front of H2O to make 12 hydrogens, coefficient of 6 in front of our reactant H2O, you see hydrogen, crystal hydrogens, we have hydrogen here and there is hydrogen here. in methane gas. 3 times 4 is 12 hydrogens. Look at the product side. Crystal, look at the product side. We have hydrogen. Look at my PowerPoint slide. We have hydrogen here and we have hydrogen here. So if I have 4 here, look at the whiteboard. If I have 4 here, the 4 will multiply the 3 here. 3 times 1 hydrogen. 3 times 4 is 12. And if I already had 3 here to balance the carbon, 3 times 4 is 12. 12 plus 12 is 24, and we want to make it so. That is what it is. Please check again. That is why it is 24. We have 24 hydrogens on the product side. And if you put 6 right here in front of H2O, you'll end up with only 12 hydrogens. We have 2 portions of hydrogens right here. Jennifer, we have hydrogen here and we have hydrogen here, and it will impact how we handle this side. So that's why we say it's 12. So coming back to the equation here, it is already balanced. It is already balanced. Before we look at, you know, the section 12 point, not 12, but 3.2, and some pattern of, you know, simple pattern of chemical reactivity, I want to show you an example on how you, all right, how you use polyatomic ions instead of splitting into single element. I may have lead 2, let's see, lead 2 nitrate. I can have this lead 2 nitrate, and it is aqueous plus potassium chloride, and this is aqueous, to form lead 2 chloride, all right, lead 2 chloride, and this is solid, plus potassium nitrate, potassium nitrate. I've just given you an example on a worded problem so that, you know, practice, but you should know. Chemical formula for nitrate, you know, what does the Roman numeral tells you, all right? This means lead 2 is, has a charge of positive 2. Nitrate is a polyatomic ion with an overall charge of negative 1. Potassium is in group 1, so positive 1. And chloride is in group 7, negative 1. Lead 2 chloride, that means PP2 positive, and the chloride is negative. Potassium is positive. Nitrate is, I'm just giving you pieces you need to form the chemical compound. I'm writing pieces, just putting pieces on the table to write the equation. Because of what you have below each symbol, this is the formula for lead 2 nitrate, PP. This is lead 2 nitrate, and it is aqueous. Using the crossover rule, this is polyatomic ion plus potassium potassium chloride, and it is aqueous. If I go back, I'm just writing the correct formulas of my reagents. Crossover rule. To form lead 2 chloride, that is lead 2 chloride, and it is solid, plus potassium nitrate. If I go back again, the crossover rule here, positive 1 and negative 1 cancels out. Positive 1 and negative 1 cancel out. Lead 2, this is positive 2 and negative 1. Use the crossover rule. I'm using the crossover rule. When I end up with that, that is the equation we need to balance. You balance if polyatomic ion appears on either side of the reaction arrow doesn't change, you balance as if it is a single entity. For example, I can read this as 2 nitrates. I have 1 nitrate on this side and I need a 2 in front of potassium nitrate. 2 in front of potassium nitrate to balance the equation. Maybe I can use a different mark, different color to write. So I'm gonna put a 2 in front of potassium nitrate. So that 2 nitrates, 2 nitrates. I'm reading as 2 nitrates, 2 nitrates. And the nitrates are taken care of. Nitrates are taken care of. 1 lead on the product side, 1 lead on the reactant side. Product and reagent, lead balances out. These 2 potassium, I have 2 potassium on the product side. I have 1 in front of, no, 1 on the reactant side. So I'm gonna need the 2 in front of potassium chloride, and the equation is balanced the way it is. What I've done is I balance polyatomic ion as if it is a single element. Instead of just taking care of, nitrogen, deal with nitrogen alone, and then you deal with oxygen alone, and then it's gonna be 2 pieces on the table for you to work with. Too much or too many pieces of element on the periodic table, which will, all right, too much on the periodic table, not periodic table, but on the table for you to work with. So balance a single, or if you have multiple polyatomic ion, balance as if it's a single unit. Let's look at the simple pattern of chemical reactivity, types of chemical reaction you will encounter, and there are about 6 chemical reactions you will see in chemistry. But as far as we are concerned, we will look at the 3 types of chemical reaction: combination reaction, decomposition reaction, and combustion reaction. Combustion reacting with oxygen. To start off with the first one, in combination reaction, all right, combination reaction, 1 element, all right, I should have right here, combination reaction. It means 1 element is produced from 2 or more, all right? We can even 2 or more to produce 1 product, and you may have, physical state of each one of them. 1 product is produced from 2 or more substances coming together. You combine. Decomposition reaction is the opposite, all right? To decompose is to break down. Decomposition reaction, that means simpler substances are produced from a single, all right? A single element or a single compound breakdown to 2 or more. It can be even more, it can be more than 3. It can be more than 3, just to give you generic states. Decomposition reaction is opposite of combination reaction. We're gonna talk about metathesis, double replacement reaction in chapter 4, but just understand the difference between combination, decomposition, and then we have combustion. Combustion is when you have this combustion, it's burning with oxygen. This is basically reaction with what? Reaction with oxygen, and mostly oxygen gas. We'll see those reactions where oxygen is involved, one of the products. So here is just example or generic way: combination, 2 or more producing 1. Example is oxygen reacting with carbon to form carbon dioxide. All right, combination reaction. All right, 2 or more substances combined to produce 1. Those are examples of combination, decomposition, and combustion reaction. Combustion reaction. Now, in combination reaction, we will see the combination when a non-metal and a metal react. I've underlined the word metal and a non-metal because we covered that in chapter 2. You should be able to classify an element on the periodic table as a metal or a non-metal, you should be able to predict the ionic charge, all right? And with that, you should be able to predict the product. For example, here on the PowerPoint slide is a combination between magnesium, and this is solid, plus oxygen gas to form magnesium oxide. Somebody might say, all right, I'm just slamming them together to form MgO2 like that. And you think that that is how to combine? No, 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 this is wrong. When you look at the metal and the non-metal, you are expected to see behind the scene the ionic charges. That magnesium is in group 2 and it has a charge of +2. Oxygen is in group 6 and it has a charge of -2. When these combine, they form magnesium, and the 2 there. Remember, you simplified, you can still simplify that, and the correct formula for magnesium oxide is this. This is the correct formula for magnesium oxide. So we just talked about the balancing the equation. So if I know this is reacting, this is a metal, solid, plus oxygen gas, and the correct formula for my product is MgO, that is not the end of the game. You have to balance the equation. This is solid right here. The equation is not balanced. We just talked about balancing the equation. So we need a 2 in front of magnesium oxide and in front of magnesium. So for metals and non-metals, you have to know, all right, you have to know the group number. For non-metal, you have to know the group number and then predict the ionic charge. And then you use the crossover rule for the correct formula for your what? For your product. And then now you balance the equation. You balance the equation. Well, there are some metals which form, you know, more than one charged particles, such as lead 2, lead 4. There is iron 2, there is iron 3, all right? Pay attention to Roman numeral in parentheses to predict the ionic charge of your metal or cation in that case. For decomposition reaction, all right, for decomposition reaction, there are 2 categories of decomposition reaction I want you to understand, all right? But before we look at specific of those types of decomposition, application of decomposition reaction is in the automobile airbag. We are all familiar with the airbags. We know what the purpose is, why they put it in there. In case you didn't know, they put sodium acide, a product of sodium and nitrogen. And upon slight ignition, it produces nitrogen gas, which inflate the airbag. Nitrogen gas inflate the airbag as a result of decomposition of sodium acide. All right. Here are just a few examples of decomposition, but the key thing is understanding that you need to balance the equation. You need to balance the equation. There are 2 types of decomposition reaction you need to pay attention, and this is decomposition of hydrogen carbonates, which means they have this ionic compound. This is hydrogen carbonate. And carbonate, all right, carbonate, decomposition of carbonates. And the formula for carbonate is CH3. The metal carbonate, metal here, it could be group 1, which means the metal will have a charge of +1. It could be +2, group 2, or group 3. You have to pay attention to the group number in order to know the correct formula for the carbonate, metal carbonate. And these metal carbonates decomposes to produce metal carbonate decomposes to produce oxide. All right, I could say that this is to produce metal oxide. Decomposes to produce one metal oxide. That means you have to know how to write the formula for, metal oxide. Is it group what? What group is that, so that you combine with oxygen? It also produces carbon dioxide. That means CO2. This is what you should be looking at in the composition reaction of metal oxide. It can be any of group 2, and then you balance out. This is group 2. All group 2 will follow this pattern. This is a metal oxide, and this is CO2. If I pick another example, such as aluminum, all right, aluminum carbonate. This is aluminum carbonate. 3, what will be my product? In this case, what will be my product? From what you have here, it should be, carbon dioxide should be one of them, and then the metal oxide. So my metal oxide will be Al, and then 2 coming from oxygen, and the 3 is coming from aluminum. This is the metal oxide. If you look at the calcium oxide, it's not always going to be the same. It varies from a metal to metal. In my example here, aluminum is +3. You have to write the correct formula for your metal carbonate. And this is solid for all carbonate, plus CO2 gas. This is the product. You can balance out the equation. If I look at the aluminum on this side, aluminum is balanced out. Aluminum is 2 here, so that's good. I can use a check mark for carbonate, aluminum, that's take care of. Carbonate, let's see. Carbonate, I don't see carbonate on the product side, so I have to split the polyatomic ion into oxygen and carbon. So here is 3 times 1 carbon, I have 3 carbon, but I have what here? I have 1. So let me just put a 3 in front of carbon dioxide. Remember, we don't use a subscript. So I'll say that carbon is taken care of, carbon is taken care of. How about oxygens? Oxygens is 3 times 3 is 9, so I have 9 oxygen on the product, on the reactant side. 3 oxygen on the reactant side. 3 oxygen on the reactant side. Aluminum, the coefficient of aluminum is 1 at this time right now. Christian, before even we finished, aluminum has a coefficient of 1, but the subscript is 2, so we say 2 aluminums and 2 aluminums. 3 carbons, 3 times 1 carbon, 3 carbons, and that's what I've taken care of for that. What I was looking at is oxygen. 3 times 3 is 9. So I have 9 oxygens on the reactant side. Versus what? Let's see on the product side. 3 plus 3 times 2. Remember, this 3 does not apply only to carbon. It also applies to oxygen. So you read this as 3 times 2 is 6 plus 3, and then it adds up. So 9 oxygen. The way right down, the balanced equation is 1. That is my 1. Maybe I should have just used, some people get confused with my 1. I should be just say 1 there, and there is 1 there. All right. The coefficient is 1 to 1 to 3. The coefficient is 1 to, we say 1 to 1 to 3. These are the just coefficient in the balanced equation. Be careful when you are dealing with decomposition of metal oxide. It gives you carbon dioxide and metal oxide. You got to write the correct formula for the oxide, and then you balance the equation. So all of them should give you carbon dioxide gas. Carbon dioxide gas. For hydrogen carbonate, you see hydrogen carbonate, you end up with H2O and metal, say hydrogen carbonate. Hydrogen, this will be metal hydrogen carbonate here. It should be metal, let's see, for metal hydrogen when this one decomposes, before we look at the combustion, this gives you metal oxide plus H2O plus CO2. So these are the two common. The other one was metal oxide and and CO2, but for metal hydrogen carbonate, it gives you metal oxide, H2O, and CO2. Decomposition of potassium hydrogen carbonate, for example, will give me metal, which is, this is the metal oxide, solid, plus H2O, plus CO2. CO2, three things. This is common, and that is common, CO2. And then you balance the equation. I do have one calcium and 2 right there. So we need a 2 in front of, let's see, in front of potassium hydrogen carbonate. And this is solid. So I read this has 2 potassiums. It's taken care of that. It's taken care of that. 2 applies to every element on the reactant. 2 applies across the board. So I read this as 2 carbons. I have 1 carbon on the product side. So let's put a 2 right there. I put a 2 in front of carbon dioxide so that carbon will balance out and carbon will balance out. How about hydrogens? 2 times 1 hydrogen, 2 hydrogens, and then 2 hydrogen on the product side. So hydrogens are taken care of. How about oxygens? If you look at oxygen, 2 times 3 is 6. And I have here 1 plus 2 is 2. No, 1 plus 1 is 2. My mind is on overdrive. 1 plus 1 is 2 oxygen. And this 2 times 2 subscript right here is 4. So 4 oxygens plus 2 is 6. And the equation is balanced. What I wanted to point out is this is the common. This is common for all. This is common for all hydrogen carbonates. Hydrogen carbonates. Oh, Anthony, so every metal hydrogen carbonate resolves in H2 and CO2. Thank you. Yes, yes, that's absolutely right. And pay attention to ionic charge for the metal. So if I pick group 3, if I pick group 4, if I put transition metals, you got to pay attention to that. So those are the 2 decomposition reaction you have to pay attention, and also you balance the equation. Hydrogen carbonate and carbonate. Hydrogen carbonate and carbonate. Any question on decomposition reaction? So when we talk about decomposition reaction, I will study on decomposition of metal carbonate, decomposition of hydrogen carbonate, and balance the equation. You still need to use what we learned in chapter 2, writing the correct formula, using the crossover rule, using the periodic table to predict the ionic charge, all right? Now, combustion reaction, did I talk about the, let's see, did I miss something? Let's talk about combustion reaction. Combustion reaction is a reaction where oxygen is involved. You know what combustion is? Oxygen is involved, all right? An element combined with oxygen, it is not hard. And mostly of the combustion reaction you see is combustion of hydrogen or hydrocarbons. Combustion reaction prediction, these are combustion of hydrocarbons. Let me say combustion of hydrocarbons. Hydrocarbons are compounds which contain element, carbon, and what? And hydrogen. All right. This is an hydrocarbon. 3-propane. This is propane. All right. And sometimes they might have oxygen, but this is an hydrocarbon. When burning compounds containing carbon and a hydrogen, they always give H2O and CO2 gas. And this is liquid, it might sometimes be gas. So that's what I'll be looking for in the combustion, all right, in the combustion of hydrocarbon, This is propane, all right. And the product here is CO2 and H2O. What you'll have here is one of the product is a reagent is oxygen, and it's oxygen gas, all right? It's not oxygen atom. You're gonna have oxygen gas. Here could be any element or any compound sort of with 2 elements, hydrogen and carbon. I've seen problems, all right, before we look at that, I've seen problems where you are asked to find, you know, the formula for hydro or carbon, the formula for hydrocarbon, but ours is only looking at the equation and say, is this decomposition, is this combination or combustion? Here is an example, typical problem you'll see in the upcoming exam. I'm gonna ask you, can you classify the equation? But for this problem, you are expected to balance and state whether it is combustion or decomposition or combination. Well, for practice, I'll only do the first one. Try the second one and the third one. The first one, that is decomposition by classifying. This is decomposition because one compound is breaking down into 2 compounds. So that one is taken care of. And balancing out, I see there is 1 lead, there is 1 lead. So if I write this is lead carbonate. And remember, carbonates give you metal oxide, and this is lead 2 oxide. This is lead 2 oxide. This is solid plus CO2. This is CO2. Lead, you have 1 lead, we have 1 lead. Oxygen, carbon, we have 1 carbon, we have 1 carbon. Let's see, oxygen here, we have 3. 2 plus 1 is 3. Everything's look balanced, so it is 1 to 1 to 1. That's just the mole ratio. We're gonna come back to that. You'll do the same thing for B and C, but when I look at this is combustion, this is combination. This is combustion, this is combination. Please try on your own this and make sure that the atoms balance out correctly. Balance out correctly. Any question on predicting the pattern in chemical reactivity? Remember the pattern. Pattern has is a trend. We see that hydrogen carbonate gives H2O and CO2 and metal carbonate. There's a pattern right there. Combustion, that's oxygen, and combustion of hydrocarbon give H2O and CO2. the composition of carbonate, metal carbonates, gives you metal oxide and CO2. And behind the scene, you should be able to balance the equation for that. Let's shift gears to formula units. And formula units, I mean formula weight, not formula unit. Formula weight is simply the weight of the weight of the chemical formula. From the word chemical formula, this is the formula for what? For sodium chloride, I mean for table salt. This is the formula. Using the periodic table, or rather, if I can, using the periodic table, look at the atomic mass of sodium, atomic mass of chlorine. If I take one sodium, if there's a way, I can take one sodium and one chlorine atom and weigh them, you end up with what we call formula unit. And we use AMU, atomic mass unit, when you are dealing with atoms. We're gonna talk about the molar mass later on. I know when we use this, all right, you may think, what's the difference? Is when you're looking at the formula of a compound, atomic weights of atoms. Remember atom, one atom. Here is one atom of sodium, one atom of chlorine. I use the same numerical value of the periodic chart, and I say this is one AMU. We use AMU to quantify that. Sodium is one AMU. Why are we using grams sometimes? We're gonna talk about the grams later on, but when you are talking about one atom, you use AMU. And remember one AMU, I don't expect you to remember this kind of equivalent statement. I talked about this in dimensional analysis. One AMU, atomic mass unit, equals to 1.67 times 10 raised to negative 24 grams. This is, you can relate to grams. I know you know the grams, but this is a small number. So the point here is when we're talking about a simple compound. We'll talk about the grams later on. Why are we using the AMU here is because of the atomic mass unit. We take 2 hydrogen atoms, 1 sulfur atoms, and 4 oxygen atoms. Using the numerical value on the periodic table, this is 1 AMU, all right? Question is it always 3 significant figures, 2 significant figures? You will have to go with what you have on the multiple choice. You may have 4 significant figures to work with that. So when we use AMU, it means you are taking only 1 atom at a time. Look at the formula. Molecular weight is the same as the formula weight, except that, you know, from the word molecules, remember molecular compounds are those compounds made up of non-metals. We use the same approach, use the periodic table. This is a molecule. This is the sugar molecule. Yes, this is some sugar molecule. Think so? And if I add up the atomic masses of 6 carbons, 12 hydrogens, and 6 oxygens, you end up with a molecular weight. And the unit is AMU, atomic mass unit, which means you only took 6 atoms. We're gonna change the equation to grams later on, and I don't want you to get confused and say, when do I use AMU? When do I use grams? We will use the same numerical value, but the units here will change in a moment when we talk about the mole. I haven't talked about the mole. So when we talk about 1, you will be able to do that. Let's see, I was testing you here. or just raising a red flag that still from chapter 2, you should be able to write the correct formulas of your compound. And I designed these examples so that you should be able to go back again. Polyatomic ions. I have a couple of resources on module 2 on polyatomic ions. In this one, you are expected to know that chromium is positive 3. I meant to say positive 3 here. And sulfate is polyatomic ion with the negative 2. So this is the chemical formula for chromium 3. If you don't end up with the correct formula for your compounds, all right, it doesn't really matter whether you understand the formula mass calculation, all right, and this is 3 right there. This is the correct formula for, that is the correct formula for the chromium 3, and you're gonna write the correct formula first. Right here, chromium 3 sulfate. This is the chromium 3. This is the sulfate. Don't think that this is sulfur. No. You should be able to use the index card, please, to memorize those common ones, all right? Carbonate, sulfate, nitrate, you will see those, hydrogen carbonate, and all those, phosphate, phosphide, so that when you are presented with these problems, you will be able to write the correct formula. I'm using the crossover rule here, which we learned in chapter 2. I showed you that. So if I write 2 chromiums right here, is it 2? Yes, 2. It will be 51.996 times 2. I'm getting these values of the periodic table. I'm getting this is from the, this is AMU for 2 chromiums, for sulfur, I have 1 sulfur, and the atomic mass of sulfur is 32, all right, 32.065. I'm using the periodic table times 3 sulfur, and this is 91.195. And oxygen here, I'm just approximating that to 16.00, 15.99, you know, you can use whatever you have on the periodic table, and this is 192 even, 192 even. If I add all of them, I end up with 387.1. This is 187 AMU for atomic mass unit, That means when I take 2 chromiums, 3 sulfur, and 12 oxygens, take their masses using atomic mass unit, I end up with the atomic mass. You'll do the same thing for second element and the third one. The second one, phosphorus, that is the chemical trichloride. That means you have 3 chlorines, trichloride. Use the periodic table. Potassium, permanganate. Quite often I see students, you know, they don't learn their periodic table, and they assume that this is magnesium. They use the atomic mass of magnesium for manganese. No, it's make sure you know your compound. So that's what I want you to know as far as calculating the atomic, or not atomic, but the formula weight for ionic compounds, or molecular weight for molecular compounds. Now, percent composition is simply determined by looking at calculating the atomic mass or formula mass, all right, or molecular weight of your compound. From the previous example, we calculated the atomic, the molar mass, not molar mass, but the formula mass of chromium 3. If you are asked to find the percent composition, is the percent of the element of the formula weight of the compound. We saw in the previous section how to find the formula weight. Number of atoms times the, all right, at number of atoms times the number of atoms. Number of atoms times the number, no. There's a typo here. This should be, all right, percent element, I'm gonna change that. is given by the number of, this is given by the number of atoms times the atomic weight of that element, you're multiplying by the atomic weight, not atomic number, it doesn't make sense. Atomic weight times the number over the molar what? Over the molar or formula weight, which we determine. For example, percent chromium in the previous example right here. In this example, this is the formula. You see here, this is the formula. If I am looking for percent chromium in this compound, it will be, percent chromium will be 2 chromiums times 51 point what? 996. This is the atomic mass or atomic weight of chromium all over the formula weight, which is 387, all right, 0.187 times 100 to change to percent. Don't forget that percent. Don't forget that percent. And I should have my calculator, looking for my calculator to do that calculation. All right, so 51.996 times 2, all right, divided by 387.187 times 100%, 28.9. I can say this is 28.9%, just to give you, what to remember, how to find the number of atoms. Subscript, if I have something like percent of sulfur, for example, if percent of sulfur in this case, the subscript 3 here, I'll have 3 sulfur. So if it is percent sulfur, you'll have to do the same thing, multiply by 3, and then you divide by that to get the percent sulfur. So change this. I know it doesn't make sense. I should have captured this in PowerPoint slide. I'll change before I repost this to make the correction. So that number of atoms, it should be the atomic weight. Look at my whiteboard, atomic weight of that element times the number of atoms in the compound over the molar mass. It starts great, it's easy. Percent of carbon in the glucose. This is the same compound. You're wondering where is 6 coming from? Glucose. Let me back up to this compound right here. This is the glucose. 6 of them. 6 carbon. This is the atomic, the molecular weight of glucose. So there is 6 times 12 atomic mass unit over 180, and then you end up with that. That is how to find the percent composition. It's tailored, or to formula weight, molecular weight of compound. It's easy. Yes, that. Any question on that? All right, real quick, this is the last item I want to look at, section 3.4, Avogadro's number. What is Avogadro? Or who was Avogadro? Avogadro is a scientist who worked with different gases, and every time he was counting the number of atoms, he ended up with a numerical value, all right? A numerical value we call Avogadro number 0.22 times 10 raised to positive 23, working with different gases, counting them in a certain number of moles. He ended up with this we call Avogadro number. Avogadro number is used to express the number of atoms, which is equivalent to this numerical value. There's a term here you are seeing for the first time, and I know you have seen it somewhere, 1 mole, all right? This is a convenient unit of measurement used by chemistry to express certain number of things. certain number of things. If I have 1 mole of students, this is the number of students I have. It's just like saying a dozen of eggs. You have 12 eggs. A cross of pencils, that means you have 144. Maybe a team of players, you know how many they are, but as far as we are concerned, 1 mole of anything contain Avogadro's number of things, which is, 6.02. It doesn't change anything if I put two to 4 significant figures or 3 significant figures. It's the same thing. It's the same thing. Ali, it's the same thing. Don't worry about that. 2, 2, 2, 1. It's the same thing. 4 significant figures. I'll use 2, 2 here and reconcile with multiple choice. For 3 significant figures, you can use O2. Or to avoid for being politically correct, let's use 2, 2. It's just gonna work the same way. And there is Mole Day. Every October the 23rd, from 6 a.m. to 6:02 a.m. to 6:02 a.m. to 6:02 p.m. That's the Mole Day, and just to celebrate Mole Day. But that is what mole stand for. 1 mole of anything represent the Avogadro number of things. Avogadro number of things. Now, molar mass now, we talked about in the previous section, formula weight. 1 mole. Give me 1 minute. 1 mole. If I have 1 mole of NaCl, that means you have Avogadro's number of these items, and it will weigh the atomic mass unit, which is grams per mole. If you look at the units right here, all right. If you look at the units right here, it is grams per mole, which is 1 mole of anything. 1 mole. If you have Avogadro number, you're gonna have the molar mass. I don't want to continue. It's now 12:30. I want to end up our lecture for today. From sections 3.4. I'll send you more information for the exam. All right. I'll send you the information for exam next week. There will be study guide. There will be formula sheet. I'll send out the formula sheet. Be on the lookout for more information. You can send me email. You can schedule private one-on-one Zoom conference. Somebody walked in today for office hour. I'll be sending out, a link before our lecture meeting from 10:50. You may see from 9, based on the course syllabus. I'll send you the link that I'll be here. Please stop by. If you have anything, I'll be more than happy to help you. Somebody is asking a question for the quiz. Did you want us use our own calculator? No, use the analog one. Even in the exam, you're gonna use the analog one. It's a simple calculation. All right. You'll have enough time to work on that. You'll have until section on formula weight and formula mass calculation. That is where the quiz will cover for chapter 3 up to wherever we covered, even the exam up to wherever we covered in chapter 3. Not the entire chapter 3. I know in the syllabus is saying 1, 2, and 3, but up to the section we covered today, not what we will cover on Thursday. We'll continue on Thursday with the lecture, but it won't be in the exam, all right? It won't be in the exam. It will be up to wherever we stop today, all right? Would there be a quiz before? Yes, there will be a quiz, a short quiz based on up to whatever we covered today. The exam, please check on the syllabus. The exam will be next week. And it's not, I will give you the time frame when to complete the exam. It's not gonna be a long time frame for that. I'll give you a shorter time to to finish the exam. Yes, you'll use a scratch paper for the exam, all right? You'll use a scratch paper, you'll use the periodic table. Please plan to print the periodic table as well. You will use the formula sheet on the exam, but not in the quiz. Yes, Jennifer, you will use scratch paper. You will use the periodic table. You will use analog. And then the exam is next week. Next week is the exam. If there is no other question, I will stop sharing the screen. Thank you for tuning in. I hope to see you on Thursday, same time. Please plan to take the quiz, do the homework assignment, use the homework assignment as practice. You should be able to, you know, normally I make the quiz more hard, more challenging, but the exam you should do well. Thank you for tuning in. See you on Thursday, same time. The lecture is ending. Bye, everyone.